right, so we are starting a new section. We finished up our pretty thorough discussion of alcohols and ethers in chapters 13 and 14. Last semester we covered a ton of detail on IR, NMR, and mass spec in chapters 15 and 16. So that leads us now to chapter 17. And I need to share my screen. Thank you for the reminder. So in chapter 17, we're going to talk a little bit about situations where alkenes are in conjugation and what kinds of reactions that leads to, which we'll be talking about later this week in more detail. So when it comes to alkenes, we've seen a lot of examples where there's a pi bond, some R groups attached, maybe it's trans or cis, depending on what's present. But we haven't really looked at situations where alkenes kind of act in concert as one single functional group. So if I have more than one alkene, specifically a di, meaning two alkenes, diene. If I have two alkenes, then the proximity between the pi bonds has a big impact on the behavior of those structures. So there are really three options. Cumulated, we'll find, is relatively unstable. In accumulated diene, the two alkenes are coming off of the same carbon, and that's unstable relative to the other options. In an isolated diene, there's any number from 1 to more than 1, any number of sp3 hybridized carbons separating the pi bond. Right, so the sp3 hybridized carbon here means that the p orbitals of this are not close enough to overlap with the p orbitals here. So in this case, it just behaves as if we got two separate molecules, two different pi bonds that may or may not react, but they're not interacting with one another, and the presence of one pi bond is not going to affect the reactivity or behavior of the other. The conjugated situation is what we're going to focus most of our time on, because when your pi bonds are conjugated, they react together, they're more stable, so that occurs just much more frequently in nature. A lot more molecules have this feature. And the reason for that is because of the p orbitals. So the two p orbitals overlapping side by side to make one pi bond are conjugated with or connected to the p orbitals overlapping to make the other pi bond. Right? These p orbitals are on adjacent atoms. Both carbons are sp2. So these p orbitals can also overlap side by side. And that creates a molecular orbital that extends over multiple atoms. It's very similar to resonance. This extended conjugation of the p orbital side by side imparts a significant amount of stability on the structure, which we're going to talk about as we move through. So here are the p orbitals. So one thing we didn't mention about the cumulated diene is the central carbon here is sp. Right? It has two sigma bonds for which it needs two hybridized orbitals. And there are two sp orbitals for the sigma bond overlap here and the sigma bond overlap there with the neighboring carbons. The head-on overlap between their sigma between their hybridized orbitals creates those two sigma bonds. And if it's sp, that means there are two unhybridized p orbitals on this carbon. if one is in this plane, the same plane as the paper, the other has to be behind and in front. Right? P orbitals always have to be perpendicular to one another. So if we look at the p orbitals there, those are in, they're perpendicular or in different planes. Right? So one might be perpendicular to the axis of the other. All right, so there was a brief interruption there. We'll keep moving. The fact that they're in different planes means they can't overlap effectively. And it means we have a lot of pi electrons on only over 3 atoms. So that's a lot of electrons in these orbitals farther out from the nuclei where they're not attracting very effectively to the nuclei. So that's a relatively unstable situation. Versus if the p orbitals can overlap side by side all the way on top and all the way on the bottom, I can create these molecular orbitals that allow the electrons to exist in the areas of overlap, assuming there's no nodes forming there due to constructive interference, which some of the orbitals will have nodes, but there will be at least one molecular orbital where all the overlap on top and on bottom is constructive. And that will increase the electron density in the area of orbital overlap here, which will allow the electrons to attract to multiple atoms, nuclei at once. And so that's quite stabilizing. Conjugation doesn't require all the atoms to be carbon. So here I have an alkene conjugated with a ketone. Alkene, ketone, enone is a abbreviated way of showing you have an alkene conjugated with a ketone. And again, the alkene would have p orbitals overlapping side by side, and the ketone would have p orbitals. And if all the orbitals on top overlap, all the orbitals on the bottom overlap, it will create a molecular orbital that stabilizes those electrons over all those atoms at once, very similar to how resonance works. What about this structure? Well, there's an alkene over here, and its overlap is segregated from the rest of the structure. As soon as you see an sp3 hybridized atom on any side of that, that's separating that pi system from the rest of the structure's pi system. Right? So the nitrogen here is sp2, its lone pair is in an sp2 orbital, and it has a p orbital overlapping with this one. But then this carbon here is also sp2, it has p orbitals. So all of these carbons and the nitrogen all have p orbitals, and the top parts of those all overlap, and the bottom parts all overlap. And that allows for extended molecular orbitals over a lot more atoms. And especially one of those molecular orbitals will have all constructive interference, and that will allow the electrons to exist really anywhere in those areas at once, attracting all those nuclei, and also existing in the spaces between the nuclei, since in that most stable orbital holding the lowest energy, most stable pair of electrons, there wouldn't be any nodes. But we're going to talk more about the nodes and the electrons and their stabilities here as we go through. So if you want to make a conjugated diene, you can do that the same way we make any kind of alkene, and that's through elimination. If there's already an alkene present, you might say, well, I've got a beta hydrogen here and a beta hydrogen here, so maybe we'll just say, for the sake of argument, this had a solid wedge. So we'll be looking at the dashed wedge hydrogen there. And this bond could rotate a little bit, so the bromine and this hydrogen were anti-periplanar. So you really have two hydrogens that are anti-periplanar, but if the negatively charged oxygen here were to pick off this one, which would be less likely in part due to sterics, but way less likely, more so because if electrons were to swing in and push out the bromine, you'd make accumulated diene, right? Because there's already a pi bond there. If you formed another pi bond, that carbon is not very stable. The electrons are not all in the same plane. This p orbital would be in one plane, and the other p orbital would be perpendicular to that. They wouldn't be able to overlap on all of the atoms involved. So it wouldn't do that. As it starts to form the second pi bond there, it would be going through a much higher energy transition state, so that would not be likely to occur. So instead, the base would just pick off this hydrogen, swing electrons in, and push out the bromine, and you'd form the pi bond over here. And so if you're going to do an elimination of two, to form two alkenes, so if there's already one there, or if we're forming both at the same time, what you'll see is the molecule will usually naturally form a conjugated diene because of the extra orbital overlap that occurs not just between the carbons that are involved in the pi bond, but also between the carbons that happen to both be sp2 and have p orbitals on them that are close enough to overlap, even though there's no pi bond shown in that area. Right, so the extra p orbital overlap over all the atoms makes it more stable as it's forming and as a product. So that naturally more stable state creates a situation where if the elimination is going to occur, it will typically occur in a way that leads to that conjugated product by doing the elimination in a way that puts the alkenes separated by only one single bond. So all the atoms are sp2 and all their p orbitals can overlap side by side. As we were saying, anytime atoms are sp2, they have sp2 orbitals for their sigma bond. Right? So normally if I had sp3 hybridized atoms, they'd have sp3 orbitals that would overlap to make the sigma bond. Here, there are sp2 orbitals to overlap head-on to make the sigma bond. Right? So we could talk about the p orbitals and the pi electrons, but there's also a difference for the sigma electrons. Right? A sigma bond is the single bond where the head-on overlap, where the molecular orbital that's stabilizing the electrons creates constructive interference, so the electrons get right in the area between the two nuclei so they can attract effectively to both nuclei. Not all carbon-carbon sigma bonds are equal in strength or energy. If the nuclei are farther apart and the electron density is here, it's not going to be as stable as if the nuclei can get closer and put the electron density closer to both positively charged nuclei. So what we're looking at here is a situation where when the hybridization of the atom is different, the orbitals have slightly different shapes, right? The S is more compact, the P is more elongated. So when you mix S and P to make these hybrid orbitals, the more there is S mixed in as a ratio, so this one's 50% S, 50% P, it's more compact. If I have one that's only 25% S, 75% P, it's more elongated. So what that means is in a sigma bond between two carbons that are both sp2, they both have these relatively compact sp2 orbitals overlapping head-on. And that allows the electron density to get pretty close to both nuclei. If they're sp3, then their hybrid orbitals are a little bit longer. So that'd be a slightly more elongated orbital, and this one would be a little bit more elongated. So there's plenty of orbital overlap, and the electron density can still get in the area between the nuclei to attract. It's just that the distance between the nuclei is a little bit greater. And with the shorter distance between the nuclei, the electron can more effectively attract to both nuclei in the area of overlap. So that creates an additional stability, and that we don't have that in either of these other situations. In the isolated, there's an sp3 here. The sp3 carbon overlapping with the sp2, the carbons aren't going to get as close together as if they would as if they're both sp2 with the shorter, more compact orbitals to overlap in there. So we get the more stable sigma bonds. We have a larger number of more stable sigma bonds as well than we have over here, right? There's only two sigma bonds connecting there. So that's not going to be as stable as we have multiple extra stable sigma bonds that result from relatively compact orbitals overlapping head-on. So there are really two components that two factors that affect the stability of a conjugated diene. The extra stable sigma bond due to the shorter bond where the electrons can attract more effectively and more closely to both carbons, as well as the extra p orbital overlap that creates extended molecular orbitals for the electrons above and below to attract to more nuclei at once. And that can be measured experimentally. Right? So let's talk about how to measure the stability of conjugation. When the alkenes are conjugated versus not, what's the difference in stability? Right? So we just explained why it's more stable. Now we want to quantify it and show that that can be verified experimentally. So here I have a single alkene. So to make this a fair comparison, I need two of these. So basically what we're saying is here we got two alkenes, and we want to hydrogenate both of them. You're going to add hydrogen across the alkene. This would be done with a platinum or palladium or nickel catalyst, but that only affects the kinetics. And here we're only looking at thermodynamics. So the catalyst is irrelevant. What we're comparing is what's the potential energy of these two alkenes versus the potential energy of the alkane. If we add hydrogen across here, we break a sigma bond, we break a pi bond, and then we form two new sigma bonds. So because the pi bond's less stable than the sigma bond, it's higher in potential energy. There's more potential for the electrons to rearrange and be positioned in a more stable type bond. And if they become lower in energy, it releases a specific quantity of energy, which you can measure because that energy would be released into the surroundings, causing a temperature increase in the surroundings, and that would tell you how much energy was released. So if you hydrogenate one molecule, it's going to be half that value. If you hydrogenate two alkenes, both of which are not stabilized by conjugation, it releases this specific quantity of energy. If the alkene was even more unstable, it would start higher in energy, but it would still, upon hydrogenation, produce the same alkane, so it would release a larger quantity of energy, right? So when we say a larger heat of hydrogenation, that means more energy is released when its pi bond is converted to the sigma bond, and that means it started at a higher energy to begin with. It must have started higher if it had the ability to release more. So what if we did this on this alkene? Instead of one butene, maybe we worked with two butenes. So let's say we took two butene, we took two of those, and we added hydrogen to produce an alkane. Would that release more or less than 254 kilojoules per mole? Well, in OChem 1, we talked about the stability of the alkene. Is it in part affected by the number of hydrogens bonded to it versus the number of carbon groups? So if there's more carbon groups and fewer hydrogens, it's more stable. So we could verify this experimentally. If we started with two butene versus one butene, it's more stable and lower in potential energy to begin with. So it wouldn't be able to release as much as the molecule that started with more energy. So the heat of hydrogenation for this, if you measured it, would be a little bit lower than 254 kilojoules per mole. All right, so this is how we quantify the difference in stability for alkene. So let's look at a comparison between two molecules of alkene. So this is the equivalent of converting 2 pi bonds into sigma bonds. 2 pi, we're losing 2 pi and we're creating 2 new sigma bonds because we're doing it twice. Versus a single molecule of this, which happen to have 2 pi bonds. So if I just look at one of these versus one of these, well, this is going to be less stable because there's 2 pi bonds versus only 1. Right? This molecule here has more sigma bonds than this one, so it's more stable. But it's not a fair comparison. We want to compare the stability regardless of the number of pi bonds. So I'm starting with 2 molecules. That way I have 2 pi bonds, then I'm going to convert into 2 sigma bonds. To compare that fairly, I only need one of these molecules because it already has 2 pi bonds. And I'm going to add hydrogen across both those pi bonds to make the same alkene. So in either way, I'm converting 2 pi bonds into 2 sigma bonds. That makes it a fair comparison. When I do that on these 2 alkenes, it releases 254 kilojoules per mole because it starts off 254 kilojoules per mole higher in energy than the alkane due to the instability of the pi bonds versus the sigma bonds. And in this structure here, it only releases 239 kilojoules per mole because it starts lower in energy. And the difference between those values is 15, right? Subtract this minus this to get 15. So these 2 pi bonds happen to be 15 kilojoules per mole more stable than these 2 pi bonds because they don't release as much energy when they're converted into sigma bonds. So that allows me to quantify the stability associated with the extra strong sigma bond due to the tighter orbital overlap, this more compact orbitals holding everything closer together, as well that in combination with the orbital overlap between the pi bonds. We already know there's orbital overlap between p orbitals when a pi bond is formed, but there's also orbital overlap here. So there's no pi bond here, but there's still orbital overlap. So there's still going to be some electron density that can attract to both those carbon atoms in the space between them where the orbitals overlap. So the extra p orbital overlap and the extra strong sp2 head-on sigma bond overlap makes this a little bit more stable than the other isolated alkenes versus the conjugated alkenes. And so that's really the answer to the first quiz question. Right? So I'll give you feedback on your answers, but the gist of this is heat of hydrogenation is exothermic because you're converting a pi bond to a sigma bond. So what are the factors that are going to affect the amount of energy released? 1, the number of pi bonds. If the more pi bonds converted to sigma, the more energy released. That's why in this last comparison, we needed 2 of these molecules. So we'd have the same number of pi bonds converted to sigma in both to make a fair comparison. And that way we can tell whatever the difference is how much more stable one is versus the other. But if you had 2 molecules that had different numbers of pi bonds, whichever one has the most pi bonds, it should release the most energy and have the highest quantity of heat released upon hydrogenation, or the greatest heat of hydrogenation. 2, conjugation. We just saw that. That's 15 kilojoules per mole. That extra conjugation made it more stable. So if it's conjugated, it's going to have a lower heat of hydrogenation because it's more stable. Last semester, we talked about the number of carbon groups substituted on the alkene. More carbons, more stable. More hydrogens, less stable. And so if it's already more stable, it's lower in potential energy. And so it has less energy to release upon hydrogenation. and so it'll have a lower heat of hydrogenation. And then the last thing you'd want to look at, if it's relevant, is sterics, right? So this is in order, by priority, based on which factors affect stability most. So if you have crowding between large groups, maybe if you have like a cis alkene versus a trans, if the large groups are not crowding, it's going to be more stable, lower in potential energy, and it's going to release less energy upon converting that pi bond into a sigma bond. All right, so let's apply that to this example. So we want to rank these in order of increasing stability. I might also ask you to rank them in order of increasing or decreasing heat of hydrogenation. So if we're going increasing stability, we would go from least stable to most stable. And if it's more stable, it has a lower heat of hydrogenation. If it's unstable, it's higher in potential energy, so it has the potential to release more energy upon hydrogenation. So which is the least stable, which is the most stable? We've got to look at their structures and consider the factors we just talked about. So the number of pi bonds is the biggest factor. So here I've got 1, 2 pi bonds. Here I've got 1, 2, 3, 3, and 3. So this one with only 2 pi bonds is definitely going to be the most stable. I only have to add hydrogen across this one and this one. Each time hydrogen's added across here, it converts a pi bond into a sigma bond, goes down in potential energy, and releases energy into the surroundings. So this is only going to release a little bit of energy compared to a situation where I can release more energy because I'm converting 3 pi bonds into sigma bonds. So if it only releases a little bit of energy, it's relatively stable because it didn't have a lot of energy to begin with. So A is going to be the most stable. It's going to release the smallest amount of energy because we only have to do that twice. So the other 3 have the same number of pi bonds. So the next factor we would go to is the amount to which they're conjugated. Right, so here I see in this molecule, this pi bond is conjugated with this one. They're close enough to overlap. But this one up here is isolated by a couple sp3 hybridized carbons. So it's not fully conjugated. Got a similar situation here. This one, though, is fully conjugated. Because every carbon that's part of a pi bond, every sp2 carbon, is right next to another sp2 carbon. And the p orbitals can overlap all the way across there. So that extra conjugation means that the carbon-carbon sigma bonds are more stable because they're both involving sp2 hybridized carbons that have better overlap and pulls the carbons a little bit closer together to attract to the electrons between them. And the extra p orbital overlap creates molecular orbitals extending over more atoms, so the electrons can spread out from one another and attract to more nuclei at once. So that's going to be more stable than B or C, but not more stable than A, because I still have to put in, I still release energy for every pi bond that's converted to a sigma, and doing that 3 times is going to release more energy than doing it twice. So that would mean D would be here. Comparing A and C, they have the same number of pi bonds. They have the same amount of conjugation because, 2 of their pi bonds are conjugated and 1 is isolated. And so then we look at for the number of carbon groups attached versus hydrogens at the pi bond. So let me get rid of some of this clutter, come back in. So looking at B and C, I want to look at every carbon that's sp2 and count how many hydrogens versus carbons are attached. Since these are mostly carbons, it'll probably be easier just to focus on the hydrogens. There's 1 hydrogen here, carbon, 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 hydrogen, carbon, hydrogen. So of all of the positions that could potentially bond into hydrogen, only 3 are bonded to hydrogen, the rest are bonded to carbon. When I look at this structure, I see a lot more hydrogens present bonded to the sp2 hybridized carbons. So that tells me that since B has its alkenes more substituted with carbons, and A has its alkenes more substituted with hydrogens in comparison to one another, B is going to be more stable than A. So if we're going from least stable, increasing stability, the least stable there would be C, and then B, and then D, and then A. So if you have questions about that one, let me know. So the stability of a pi system also depends on the rotation of the single bond that's connecting the two areas, the two pi areas. So since these are double bonds, they can't rotate, right? Because the p orbitals here have to remain overlapping. If you try to rotate this bond, the p orbitals won't overlap anymore. It'll be really unstable. So normally those p orbitals overlap all the way across, but that requires this single bond to remain unrotated. If you rotate this and flip it up in the air, even temporarily, this p orbital and this one won't overlap anymore. They don't need to overlap though, because there's no pi bond in there. So rotating here doesn't break a pi bond, it just breaks up a little bit of extra overlap that makes it extra stable. So I do have to put in some energy if I want to rotate that. But upon rotating here and flipping this up so it would look like this, I get an even more stable structure due to sterics, right? So the key thing here is in the S cis, so it's not cis, it's S cis. The S here stands for a single. Right, so we're talking about the rotation of the single bond. Around this single bond are the two identical groups on the same side, which is S cis, or around the single bond are the two identical groups on opposite sides, which would be S trans. Right, so comparing S cis versus S trans, the S cis has more sterics. These are only hydrogens, and if there were larger groupings of atoms, there would be even more sterics. But with a small hydrogen atom, even then, they're pointing right at one another, and so their electron clouds start to overlap and create some repulsion. Here, I don't have that. Everything's much more spread out. So that's why the S trans is more stable than the S cis. What about other rotational conformations? Well, if one alkene is in this plane, and the other alkene rotates into a different plane, how's that going to look stability-wise? All the alkenes are just as stable, but the area between them is not as stable, right? So when you have the S cis or the S trans, the p orbitals overlap all the way around. They're all in the same plane. When you are rotating somewhere between those two, the p orbitals no longer overlap because they're not in the same plane side by side anymore. And so that's especially unstable. And so we could look at an energy diagram here once we talk about the p orbitals a little bit more. Right, so this shows the p orbitals overlapping in the S cis and the S trans. They're also overlapping. What other conformation would there be, and would that be higher in energy? Yeah, it would be, right? So obviously, if the single bond between the two pi bonds rotates so that the pi bonds are not overlapping anymore, that's your highest energy point around that rotation. Right? So rotation that creates full orbital overlap all the way around is going to be significantly more stable than losing that extra orbital overlap, right? Because when the orbitals overlap, there's going to be more ability for a molecular orbital to create electron density in that space to attract to those atoms. There's no pi electron density here when the orbitals, the p orbitals can't overlap. So that's what we're talking about. This graphic here is what we're talking about right here. What other conformations are there? There's other conformations where the p orbitals of the two pi bonds don't overlap. And that would be higher in energy, right? Because the extra orbital overlap that would occur if everything's in the same plane and all the p orbitals are side by side allows the electron density to spread out over more atoms and be attracted to more nuclei. When you have a 12 kilojoule per mole difference, that's a pretty decent difference. As we said, that difference is due to the sterics associated with the hydrogens pointing too close to one another and their electron clouds overlapping, creating some repulsion. It's definitely less stable than it would be if we avoided that sterics. But due to the p orbital overlap all the way around, it's still more stable than it would be at the highest energy point if you were to rotate that single bond, so you'll lose that overlap. So if the 12 kilojoule per mole difference means 98% of the molecules are in this form, and the rotation to create the other form only happens once in a while, and when it does, it rotates back pretty fast, so only a small fraction of 2% of the molecules actually exist in this form at any given moment in time. The number that would exist in this form would be way less than 1%. So you have a tiny, tiny, tiny fraction of the molecules caught at a moment in time looking like this. And that's the power of that p orbital overlap. Rotating everything into the same plane so that the p orbitals can overlap all the way down the structure really does create some especially stable molecular orbitals due to all the extra orbital overlap, which we're going to see in more detail. And so we want to talk about those molecular orbitals and explain why they're stabilizing to the structure. We'll do a little review here of what molecular orbitals are and how they form. So if you remember when we talked about molecular orbitals, we said they form when atomic orbitals overlap, right? So if we're looking at a pi bond, it would be the two p orbitals. And if there's an area of overlap, if both of those p orbitals have the same wave sign, so not the same charge, it's not an electrical charge we're talking about here, we're talking about the mathematical value or sign, positive or negative, for the wave function, which is a mathematical expression of the electron. If they have the same wave sign, then they constructively interfere, and that gives a bonding molecular, right? So the electron density increases in the area of overlap, and that's more stable. That's where the electrons go. That's the bonding molecular orbital. Normally, we don't even worry about what the antibonding looks like because it's too unstable for the electrons to usually go in there. So why are the electrons more stable in this bonding molecular orbital than they would be in the individual atomic orbitals? Well, in the individual atomic orbitals, if an electron is in here, it can be up here, it can be up here. It can only attract to one nucleus. Once the orbital overlap occurs, and the electrons can now exist in this bonding molecular orbital, they can exist all over here. And they can get into this area here where they're close to both nuclei at the same time, and they can attract to both nuclei. But anytime orbital overlap exists, we get every possible combination of wave signs. So there's going to be constructive interference as well as destructive interference. So if the two wave signs are opposite, then their waves cancel. In the area of overlap, I get zero electron density, and that creates a node. And so that's especially unstable because the electrons are only going to be in these areas here, 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 and here, and that precludes them from being anywhere in the area where they can get close to and attract to both nuclei. So for ethylene or ethene, the electrons exist in the bonding molecular orbital. They exist here because even though both orbitals form, when they go into this orbital, they can attract to both nuclei much more effectively. More attractions in the bonding molecular orbital. And a node, in this case, is an area where the electrons cannot be due to the fact that the wave signs have canceled. The wave is what the electron is. It's acting as a wave, and if you cancel out the wave, you've canceled out the electron in that area. So nodes are bad for electrons. They make them less stable. Fewer nodes is better because the electrons get into the area of orbital overlap. The electron probability increases when the wave signs add together constructively, and so there's even a higher chance that the electrons will be in this area close to the nuclei. So what if I have a conjugated die? Well, if I have 4 carbons instead of just 2, and there are pi bonds here and here, that would create a situation where each carbon has sigma bonds, but also a pi bond over here where the orbital is overlapping, and a pi bond over here where the orbital is overlapping. And even though there's only a single bond between the middle 2 carbons, they're both sp2, they both have p orbitals, and those p orbitals, assuming that they rotate into the same plane, sitting side by side, can also overlap and create interference. So you don't just have individual pi bonds creating bonding and anti-bonding. You have 4 orbitals now, all overlapping side by side, and you have a bunch of different combinations of constructive and destructive interference that can occur. Right, so in the most stable, lowest energy one, that's where all the wave signs on top constructively interfere and all the wave signs on the bottom match up and they destructively interfere. They also constructively interfere, sorry. So when I have full constructive interference on both the top and the bottom, there's no extra nodes, right? There's a node in the plane of the carbons, because there's always a node in that plane when I'm dealing with p orbitals. But there's no extra nodes, which means the electron density can be all over here, attracting to all those nuclei at once, and that's especially stable, which is why electrons go into that orbital first. Notice how the other orbitals each have one node more than the previous. That's a pattern that we'll see continuing, because every combination of constructive and destructive interference is going to occur here. And when we have 4 orbitals overlapping, 4 atomic orbitals overlapping, we're going to get 4 molecular orbitals, right? The number of molecular orbitals created always equals the number of atomic orbitals overlapping. When I have 4 overlapping, there are 4 possible combinations for constructive and destructive interference, each having one node more than the last, because in the first one, everything's lining up and overlapping constructively. In the next one, there's some constructive interference here and here, but then there's destructive interference there, right? So the plus minus, that cancels, and I get a node right down the middle. So it's still relatively stable for the electrons because they have lots of space to be around in, and some of that space includes the area between the nuclei where they can attract to the nuclei. But not this area. If there's a node here, they can't be in there attracting to those 2 middle nuclei at the same time. Right? So they're going to be most stable in the one with fewer nodes. Every time I add another node, it's going to be more and more unstable. And with the other combinations of constructive and destructive interference, I find this one here is an anti-bonding. Here, there's more destructive interference there is. There's more destructive interference here, 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 and here than there is constructive interference. So there's really only one area of constructive interference It's more stable than having nodes at every spot, so there's zero constructive interference, but still, if there's more destructive interference than there is constructive interference, that's an anti-bonding molecular orbital. Oops. And electrons generally will not go in the anti-bonding molecular orbital unless they are excited with energy, or unless somehow the molecule picks up additional electrons to the number versus compared to the number it would normally need to be neutral. So what we find here is if you had two isolated alkenes, then the electrons would be in this type of orbital in each of them, where they can attract to two nuclei. But if my two alkenes are in conjugation, this orbital specifically is the one that really extra stabilizes them, because instead of having two isolated alkenes where the electrons can only attract to two nuclei at once, I've got two conjugated alkenes where in one of those orbitals the electrons can attract to all four nuclei at once, and that's the extra stable one that makes this whole thing much more likely to occur and relatively stable compared to isolated alkenes. So explain why the instability of electrons in a pi molecular orbital directly relates to the number of nodes. Right, so we pretty much did that. I'm not going to go through it in as much detail as we just did, but just to reiterate a little bit, fewer nodes means more constructive interference, more areas between the nuclei where the electrons can exist. More nodes results from more destructive interference, which means there's no electron density in the areas where the electrons really are most stable, which is between the nuclei. So, butadiene. But means four, di means two, diene means two enes. So that's how we would draw butadiene. And as we said, there are four pi electrons, right? Two here and two here. And where are they going to go? They're going to go in the lowest two molecular orbitals, the ones that have the most constructive interference, and that's going to stabilize those electrons more than they would be otherwise. And this one here is the especially stable one because there's all constructive interference. That's why you get 15 kilojoules per mole extra stability associated with conjugation, right? And that's because even though there's only a sigma bond between these two carbons, their p orbitals still overlap, and that puts some pi electron density between there to create extra attractions. So we already explained why the single bond is more stable. We said when both carbons are sp2, the sp2 orbitals are relatively compact, so the electrons can attract pretty close to both nuclei. But this is another reason why that extra carbon-carbon single bond, this one here, is more stable, because not only is there good overlap between those two carbons in the sigma bond, but there's also side-by-side p orbital overlap, and that allows electron density to be in that p orbital, or in the area of the p orbital overlap that creates a bonding molecular orbital for the electrons to be stabilized. All right, so what if I had 6 carbons with p orbitals all overlapping side by side? So this would be a molecule 1,3,5 hexatriene. So hex means 6. Triene means 3 enes, 3 pi bonds. One of them starts on carbon 1 and bridges to 2. One starts on carbon 3 and bridges to 4. One starts on 5 and bridges to 6. Right, so this is the molecule we're talking about. It's fully conjugated. Every carbon in the chain is sp2. So every carbon has a p orbital, and all those p orbitals are overlapping side by side. Not just the ones that need to overlap for the pi bond, but also the ones where there is no pi bond. And as we said, that creates an extra ability for some constructive interference to occur to stabilize the electrons in those areas where we wouldn't normally expect pi electrons to be, because we're not showing a pi bond between those carbons. So if all the orbitals on top and on the bottom constructively interfere, I don't get any extra nodes. It's especially stable because the electrons can be in all these areas between the nuclei. If I have one node, it's a little bit less stable. If I have two nodes, a little bit less stable. But these are the bonding molecular orbitals. Putting the electrons in here, there's more constructive interference than there is destructive interference in each one of these, and especially this one here is especially stable because there's no constructive interference at all. This one especially is the one that really drives the stability, or creates the extra stability of the conjugation between those alkenes. And normally the anti-bonding molecular orbitals, which are up here, won't have any electrons occupying them because there's more destructive interference, and that would be relatively unstable for the electrons to get in there. In chemistry, the HOMO and LUMO are acronyms referring to the highest occupied molecular orbital, right? So the ones that are occupied are the ones that actually have electrons. And the HOMO has a couple nodes, so the electrons in there are not nearly as stable as they would be in orbitals with fewer nodes. The LUMO is the lowest unoccupied molecular orbital. So highest occupied, lowest unoccupied. It's unoccupied because there's no electrons in there. But it's got a couple areas of constructive interference, so it's more stable than the other anti-bonding molecular orbitals. So these are called frontier molecular orbitals because these are the ones where we're going to see changes occurring. If the molecule is going to lose electrons, they're going to come out of the highest occupied, the least stable one that's actually occupied with electrons. If it gains electrons, they're going to go into the unoccupied one that's lowest in energy. And sometimes an electron could get excited from one to the other. So that's what we're going to talk about a little bit here. If you hit a molecule with the right energy of light, that may be enough energy, if the electron absorbs it, to promote the electron up to an excited energy orbital, one that's normally unoccupied, the LUMO. It's normally unoccupied, doesn't have any electrons in it. So if this electron absorbs some energy, it can move up to that spot. Once it moves up there, it's no longer unoccupied. Now it's occupied. So it becomes the new HOMO, and the unoccupied orbital has higher energy than that now is called the LUMO. So if that happens, what would we expect to occur? Well, just to briefly mention, we're going to talk about this. We're going to see some examples probably on Wednesday where we can look at the shapes of these orbitals, the areas that have one wave sign or another, and that's going to help us explain some chemical reactions. So we're going to focus on that on Wednesday. But just looking at the excitation of this electron, moving the electron up to a higher energy level, a higher energy orbital, that requires light to be absorbed. And then once it occurs, it will usually quickly relax back down. And when that occurs, it'll release energy. So that opens up the possibility of spectroscopy. Remember, we talked about spectroscopy last semester. We said spectroscopy is a way of getting information about the structure based on how the molecule sample interacts with light. So if light can be used to knock this electron up here, depending on the wavelength of light it absorbs, that can tell us the energy difference between these two states. How much less stable is the electron when it's here compared to here? How much less stable is it when it's in an orbital with 3 nodes instead of 2? That can be measured experimentally by measuring what wavelength of light, which corresponds to a certain quantity of energy, is needed to excite that electron. And that's called UV vis spectroscopy. We didn't really talk about that very much last semester. We're going to talk about it more this semester. So we can measure the energy gap between the HOMO and the LUMO. How? By using ultraviolet or visible light. The wavelength of light that's absorbed can be converted into energy. So the energy of the light absorbed equals the energy gap between the highest energy occupied molecular orbital versus the lowest energy unoccupied molecular orbital. How does that give us energy about the structure? Well, what we know is if you have a pi system, let's go back here, a simple pi system, well, there's only 2 p orbitals overlapping. There's no conjugation. There's a very big energy difference between the constructive interference and the destructive interference. The more orbitals you have, the less of a difference there is. So if we look at the energy difference between these, the gap between these 2 orbitals is not a big energy gap. If you look at the bonding molecular orbital for ethene, where the electrons are in the bonding molecular orbital versus the anti-bonding molecular orbital, there's a much bigger energy difference. So the more orbitals, the more molecular orbitals you create by having more and more carbons in a line, all overlapping their p orbitals, the smaller the energy gap between the HOMO and the LUMO. And so this one here, where I just have one alkene, such a big energy difference between the bonding and anti-bonding molecular orbitals, that would require some of the highest energy ultraviolet light to excite an electron up there. But with 6 of these overlapping, that's a much lower energy type of light, the lower energy ultraviolet light side of the ultraviolet spectrum. So if you think you've created a molecule and it's got a lot of conjugation, you can verify that by putting it in the UV vis instrument. It will hit it with all the different wavelengths of ultraviolet light, and when a low energy wavelength is absorbed, that tells you that there's more conjugation. If a higher energy wavelength is absorbed, that tells you that there's not as much conjugation. So you can use UV vis light. How does that get information about the structure? If the structure has more conjugation, it's going to have a lower or smaller energy gap. So lower energy UV light will be absorbed. This leads to the idea of organic dye molecules. A lot of the clothing and other materials that you might buy that have color have dyes in them, right? There's different dyes for foods, different dyes for clothing. Some of these dyes are based on metal ions because metal ions also absorb light, but a lot of them are organic dyes, and they have these very large conjugated systems. So it could be something like this. This is just one example. So this is a simple example. So here I've got 6 atoms in this ring, 6 in this ring, and 2 nitrogens. That's a total of 14 atoms, and they're all in conjugation. So if I look at that energy difference between the one that has 14 p orbitals all overlapping side by side all over the structure, and it's all constructive interference, that's going to be very stable. And the one where there's nodes at every position is going to be very unstable, but there are going to be 14 energies. I don't know if I'm making 14 lines or not, I didn't count. There are going to be 14 different orbitals at slightly different energies. So the gap between the middle two is going to be very small. And visible light is lower in energy than ultraviolet light. So if I create enough conjugation on my molecule, and that creates enough different molecular orbitals to hold all these pi electrons, then the energy difference between the HOMO and the LUMO will be very small, and it might be just enough energy to absorb visible light in a certain wavelength. So by messing around with the structure of this, that might slightly change the energy gap. And so one molecule that maybe has some things bonded here, depending on the exact structure, it might have an energy gap that absorbs red light. And the red light doesn't reflect into your eyes, so it appears green to you. Or if you substitute different groups of atoms on this molecule in different positions, it might increase the energy gap slightly. And so maybe that absorbs blue light. And so the blue doesn't reflect off the material, and you see a reddish, greenish, or yellowish color instead. So there's an interesting relationship between the amount of conjugation, the size of the energy gap, and the wavelength of light that's absorbed when an electron is promoted up from the HOMO to the LUMO. All right, so that covers our basic discussion of UV vis spectroscopy and dyes and conjugation. And we'll come back to that a little bit later in the context of a couple other reactions. But before we do that, we want to also talk about a reaction we've already learned in the context of what happens with an addition reaction if you have a conjugated alkene, a diene or triene or something versus just a standard alkene. Right, so we learned last semester and have reviewed again this semester how HBr or HCl can add across a pi bond. And as long as I don't add peroxides, it should be a Markovnikov addition. And the reason for that is because when the pi bond picks up a proton, the most stable carbocation intermediate will form, right? It's not going to pick up a proton and add the proton to this carbon. If it added the proton there, it would pull these electrons away from the primary site and you'd have a primary carbocation. That's too unstable. So that's why we got Markovnikov addition. The hydrogen goes to the carbon that already had more hydrogens, because when electrons are pulled away from the other carbon, it's better at stabilizing the carbocation through induction and hyperconjugation. And then the Br minus that was formed as a nucleophile will come in there and form the product. So we got Markovnikov addition across a pi bond. We want to extend the idea of this reaction to a situation where, what if we have conjugated system instead of a single pi bond, which is pretty straightforward, we can predict the product for. If you have a conjugated system, multiple pi bonds in conjugation, like this diene, we want to be able to use this mechanism to understand what products form and why. Right? So what's going to happen here is one of these pi bonds is going to pick up a proton just like this pi bond picked up a proton. And it's going to happen through the most stable carbocation intermediate, just like it did before. Right? So if I think about this alkene, I still want the proton to be picked up from the end carbon, because that is going to produce the more stable carbocation. And the key here is this carbon already had 2 hydrogens, so it's picking up a third, and this carbon had 1. So it's only a secondary carbon, but it's conjugated now with the alkene, so its resonance stabilized. It's going to be much better than the alternative, right? I could imagine the new hydrogen coming in here. If I had gone through that route and added the hydrogen here, I'd be creating an additional hydrogen bonded here. Would be creating an sp3 hybridized carbon. So not only would I have a super unstable primary carbocation, it wouldn't be able to be stabilized through resonance. So make sure when you're showing these mechanisms that you go through the resonance stabilized carbocation if it's an option versus one that's not stabilized by resonance. Once the resonance occurs, or once the resonance stabilized carbocation forms, the resonance is instantaneous. Oops, I didn't move the pipe. The resonance instantly spreads out the positive charge of the carbocation over more than one atom. And so now we have 2 possible positions where the bromide could attack. It could attack here, forming this product, or it could attack here, forming this product. So we want to understand that step in more detail so we can predict the products that are going to form and why one product might form over the other. Right, so here's the first step. We said hydrogen could be added to this carbon or this one. Right, so if we imagine this one picking up the hydrogen, we'd basically get the same thing. The hydrogen would have added here, along with the other 2 hydrogens that are already on that carbon. This would form a carbocation, and that would be in resonance, right? So this carbocation and this one are not different. They're just flipped over versions of the same thing. So because this is symmetrical, in this example, it doesn't matter which of the 2 pi bonds picks up the proton. As long as the proton adds to the outside carbon so that the resulting carbocation is still close enough to the pi bond to engage in resonance, I can draw it either way. As soon as I see there's resonance, I want to recognize the different resonance contributors so that I can draw the resonance hybrid. Right? Neither of these 2 structures exists. The carbocation doesn't exist on either of these carbons. It exists on both of them simultaneously. So if I'm thinking about the energy diagram, here's a mistake I want to point out that you should avoid. We've got the alkene and the HBr at a certain energy. When the pi bond picks up a proton to create a carbocation, the carbocation is going to be significantly less stable. So what the mistake I don't want to see anyone make is to incorrectly think that the secondary carbocation is more stable than the primary one, and that the primary one won't form because it's more unstable versus the secondary one. That's not correct. It's not correct because neither of these exist. What exists is the hybrid. So if you wanted to draw the energy for that step, the starting energy would go up and it would form an intermediate at whatever the energy of the hybrid is. The hybrid is the only thing that exists here. The hybrid has a partial positive on both carbons, and its energy is the energy of the intermediate. so let's take a look at the next step of the mechanism. So once the hybrid forms, it has partial positives at both of these carbons, and so the Br minus could attack either of them, and I can get two different products. How is the 1,2 addition different from the 1,4? Well, just to point out what those terms mean is 1,2 means that the two atoms being added, the H and the Br, are adding across carbon 1 and carbon 2, right? So here's where the H added, here's where the Br added. That's a 1,2 addition. 1,4 means that the hydrogen that added and the bromine that added are adding on carbons 1 and 4, or 4 carbons away from one another. So that's the difference. It's a different regiochemical outcome. It produces two different constitutional isomers, which can have different polarities and be separated through potentially chromatography or something like that. But maybe I want to get one of these more than the other. So I want to look at the mechanism and the energy diagram a little bit more closely to see if I can control this reaction somewhat. So let's just look at the thermodynamics first. Oh, this is a different reaction. Just to point out, you can get the same thing with the bromination. Actually, let's come back to that one. Let's talk about the energies first. All right, let's take a look at this. This is going to be really helpful, and then we'll go back and look at some other examples. All right, so let's look at the product first. Why are the products unequal in energy? Why is this one lower in energy than that one? Same reaction we were talking about a minute ago. All right, so as I said, this is going to pick up a proton. Bromine's going to take these electrons. It's going to produce the resonance hybrid, right? So I'm not getting one carbocation a different energy from another. Neither carbocation exists. What exists really is the hybrid, and it has a specific quantity of energy. So if the bromine attacks here versus if these electrons shift over and the bromine attacks here, I get the two different products. But why is one product higher in energy than the other? Well, that is due to the stability of the pi bond. Right? So we said earlier, if the pi bond has more hydrogens versus carbons, it's not going to be quite as stable. So here, this pi bond has more hydrogens. This one has less hydrogens and more carbons. So that's why it's more stable in the end. So if we're just thinking about thermodynamics, if we can get this whole thing to continue to shift back and forth and eventually reach equilibrium, most of the molecules should be in this form. And how do we get a system to reach equilibrium? Time and heat. If we allow for enough time for it to reach equilibrium and maybe heat it up a little bit more so there's enough energy to keep going back and then forth and keep going over these transition states in every direction, eventually most of the substance will exist in the form of the structure that has the lowest free energy, which is the one with the more stable pi bond. So that's what I use if I want to make this one. If I want to make the other one, I can't rely on it to be formed thermodynamically because it's not as low in free energy as the 1,4 adduct. So what can I do there? Well, let's take a look at the transition states, right? Because there's a difference here. We want to understand the difference in energy between the transition states. The 1,2 adduct goes through lower energy transition states. So it will form more often, but then it'll often go back. So if I want to form it, I want to understand the difference in the transition states and take advantage of that. All right, so let's call this A and this B, and we'll draw. Let's take a look at what A looks like. A is where the bromine connects here. That's pathway A. So if I were looking at the transition state A, it would have the bromine coming in there. The bromine would have a partial negative, the carbon would have a partial positive, right? It would be in the process of attacking the carbocation. In the process of attacking, it's starting to form the bond, but it hasn't formed it yet, so I have these partial charges. In pathway B, it's attacking the secondary carbon. So that transition state would look like this, and I would still have partial charges. Right? So here, the pi bond isn't as important. What's important is I've got a significant quantity of partial charge on a carbon. The primary carbon is not going to stabilize it as well through hyperconjugation and induction as the secondary carbon. So B goes through a lower energy pathway because of the secondary partial positive that forms versus the primary partial positive that forms in the other pathway. Right? So if I want to make the one that's favored thermodynamically, I increase the temperature, allow for everything to shift back and forth over a long period of time, and eventually I'll get as much of the lowest free energy product as I can possibly make. If I want to make the other compound, I have to keep the temperature lower. Keeping the temperature lower will slow the process down, so not as many reactions will make it up here to make the intermediate, but when the intermediate does form, lowering the temperature means most of the collisions from there won't have the ability to go through the higher energy transition state, so I won't form much of this product initially. Most of the collisions that occur maybe will have the energy, though, to maybe get through the other pathway, so this will be the first product to start to build up in solution. As long as I don't add enough heat and wait long enough for that to continue to react back, and then once in a while I'll make the 1,4 and that builds up in solution, I can mostly get what forms initially as my major product. And so that's the idea here. At a lower temperature, the major product is the one that forms more often through the lower energy pathway. At the higher temperature, the major product is the one that is more thermodynamically favored because of the more substituted pi bond versus the other one. All right, so with that knowledge in hand, let's just discuss this real quick. So with the BR2, it's a little bit different. So the mechanism we know is a little bit different. Typically, when we do this bromination in the dark, we see this mechanism where it produces a bromonium ion. And we say, well, that's better than a carbocation because the carbocation doesn't have a noble gas configuration. At least here the bromine has a noble gas configuration. But when we do this experimentally, the fact that we see both of these products forming tells us that this bromonium ion isn't really the correct intermediate that it's going through anymore. If it went through this intermediate, there'd be only one place for this Br- to attack. Well, two, either here to open that up there, or down here to open this up. I would always get the two bromines on adjacent carbons, and I would always form the 1,2 adduct. But the fact that this forms at all tells me that some of this, at least, has to be going through a different mechanism. So instead of forming the bromonium ion, with a positive charge on the bromine, if the bromine were to pull its electrons away from there to leave behind a carbocation, the resonance would really help to stabilize that. And especially if I increase the temperature and allow it to eventually reach an equilibrium where it can go through this pathway and go back and forth, this might be my major product because the pi bond's more stabilized with carbon groups than the pi bond over here. So even though maybe that goes through a higher energy transition state because the attack on this primary site leaves a significant partial positive on that carbon, adding enough temperature and time should allow most of those pathways to occur and for the more stable product in the end to build up as the major product. So this is a situation where not all of the structures would go through the bromonium ion. That might open up to produce a resonance stabilized carbocation, which could then be attacked at either position by the bromine and give me a mixture of products, which I could control to some degree by controlling the temperature and the time. All right, so let's look at this example. So here we've got a bit of a tricky situation. We've got a pi system. It's going to pick up a proton. And here my two alkenes are not equivalent. So I really have to consider two options. What if this pi bond were the first one to pick up the proton? What would that give? The proton would be added there because the carbocation would need to be stabilized by resonance. Or what if this alkene picked up the proton? The proton would again still go onto the end to produce a resonance stabilized carbocation. So the first step, if it produces different structures, I really have to analyze those two structures to see which would be more stable. Because now we're looking at the first step, and that's the rate determining step. In the first step, that's where the carbocation forms. So since these two carbocations are different, and this is the rate determining step, if one carbocation forms it's higher in energy, and another that forms it's actually different and lower in energy, it's almost never going to go through the higher energy pathway. So I can really exclude that from my analysis for the most part. So what am I seeing here? Well, both of these are similar in energy. At least they're both similar in that they have their resonance to stabilize the carbocation. Let's shift it here. Get the carbocation there. The pi bond would shift over here. But there's a difference. In the structure on the left, the carbocation is stabilized instantaneously between a secondary and primary site. Here, the carbocations shared between a tertiary and another tertiary site. So this is really going to stabilize the carbocation a lot better if it's stabilized over two different tertiary sites instead of a primary and a secondary. So I can ignore this pathway now from here on out. And I can recognize that the chloride that's created here after the proton transfer, it could attack either one of these two carbons. And with similar likelihood, because they're both tertiary. And they would both produce a chlorine added there, would both would produce a pi bond that's substituted with 3 carbon groups and 1 hydrogen. Right, so if I drew these potential outcomes, the chlorine came in here, it could come in sometimes with the solid wedge, sometimes with the dash wedge, and that is a chiral center. If it came in here, again, it's flat with the carbocation, so the chlorine can come in from the top or from the bottom. So would I get 4 possible products there? Well, not really, because this structure is the enantiomer of this structure. They're mirror images. They're not superimposable, but they are mirror images. So I don't need to draw both and then the enantiomers of both, because this one, its enantiomer is the same as this one. And this one's enantiomer is the same as that one, so I don't need to draw that. There's only 2 possible stereoisomers that would occur here. And so those would be the major products that result from this reaction. And so this is a situation where memorizing the outcome of the reaction is not going to be nearly as useful to you as working through the mechanism to predict the most likely outcome, because it's the mechanism that helps you to understand that when the first proton transfer occurs, you're going to get a resonance stabilized carbocation. If there's more than one option for where that proton could be picked up, and those two options give different stabilities for the carbocation, the one that's more effectively stabilized is going to occur. And then you want to think about what would happen if the chlorine attacked either of those two positions that are sharing the partial positive, and draw the products, and then look at the relationships between the products to make sure you understand all the products that would likely form. All right, so as we were saying, drawing the transition states helps us to understand why one transition state might be lower in energy than the other. That would occur more often. So if we keep the temperature low, most of the reactions might go through there initially, and that would be our major product, which is what we're seeing here at the lower temperature. If we increase the temperature, it doesn't have to be increased a lot. Increasing the temperature will provide enough energy to go through each of these pathways back and forth, and eventually the one that's lowest in energy overall would be the major product, which is what we see here at the higher temperature. So I also would expect you, if I give you a reactant and a product, and I say, maybe you want to make this one, or maybe I want you to make this one, you'd have to also be able to describe what the temperature, appropriate temperature would be, and why the temperature would necessarily give you one as the major product over the other. So as we said before, whichever pathway is lower in energy for its transition state is going to happen more often regardless of the temperature. Even at a higher temperature, if the transition state energy is lower than the other one, it's still going to happen more often. The only thing is, with a higher temperature, is it can then also go back more often. If it's going forward more often but then back more often, once in a while after it goes back, it'll go over this higher energy pathway. And then once it gets down here, it's going to be much less likely to go back, because that's a much higher energy. It has to go up to go back to the intermediate. So that's why this product starts to accumulate over time at higher temperatures, which we just explained. All right, let's take a look at this example. So here I'm giving you one reactant. It's reacting with HBr either way, but we're focusing on how the temperature affects the second step of the mechanism that we just looked at in detail. So maybe we'll start here. And so the first step is going to be the same for both of these. In the first step, I have to consider two possibilities. What if this alkene picks up the proton versus what if this alkene picks up the proton? And so let's take a look at those. If this alkene picks up the proton, it would end up adding there specifically so that the carbocation that results can be stabilized through resonance. You would not want to show the alkene picking up the proton to produce a structure like this. And so it might be interesting to put the proton here so that the carbocation can be tertiary. That's not good. A tertiary carbocation that's not stabilized by resonance because it's not in conjugation with the pi bond, and in other words, the p orbital that's empty is not close enough to overlap and be stabilized through resonance, is not going to occur. So you definitely want to only consider adding the proton to the outside carbon of this conjugated pi system. That way the resulting carbocation will be stabilized through resonance. So that's one possibility. If the other pi bond comes in and grabs the proton, it would then be added to that carbon right here, which would make this carbon a carbocation, and this pi bond would be there. So then if this one were to be stabilized by resonance, the carbocation would be spread out over a secondary and a primary carbon. Not great, but the resonance still makes it more stable than it would be just alone on a tertiary with no resonance. Over here, the other resonance contributor would actually produce a tertiary carbocation. So this one is shared between a tertiary and a secondary. So spreading out the partial positive over a secondary and a tertiary is going to be more stable than spreading out over a secondary and a primary. So I don't have to worry about this option anymore. Now, I just have to consider, is the Br minus going to attack here, or is it going to attack here? At a higher temperature, I want to focus on which product is more stable. So maybe I want to draw those products. If the bromine comes in here, sometimes it would come in from the front, sometimes from behind. That creates a chiral center, so that would be also having half the molecules with a dash wedge for the bromine. If the bromine comes in here, that also creates a chiral center. If it comes in from the front, you could imagine it pushing the methyl group back. So that would also happen. It wouldn't happen stereoselectively. I would get equal amounts of both enantiomers there. So which is more stable? Well, once the bromine's connected, there's no large partial positive to stabilize. I'm not worried about that. I'm more focused on the stability of the pi bond and how substituted it is with carbons versus hydrogens. And at the higher temperature, I expect it to keep shifting back and forth and eventually accumulate the product that has the more substituted pi bond. At the lower temperature, though, I expect it to go through the pathway that's lower in energy pathway. I really expect it to go through that pathway first anyway, but the higher temperature, it keeps shifting back and forth and speeds up the rate at which it reaches equilibrium. So at the low temperature, I'm slowing it down so it doesn't reach equilibrium, and then I can selectively produce whichever product forms through the lower energy pathway. And that would be this product here, because what would be happening there is, as it approaches here, it would start to form a bond there, and the partial positive on a secondary carbon wouldn't be as stable as the partial positive that would form as the bromine starts to form a bond here, because that would be a tertiary carbon stabilizing that positive versus secondary. So this would go through a lower energy pathway and be the major product. At the lower temperature. Questions about that? All right, so that leads us to the last quiz question that was due today. Basically a similar situation, except here I'm just asking you to look at the lower temperature. So we want to focus on the lower energy pathway. We want to consider, since we don't have a symmetrical diene, both this alkene potentially picking up a proton as well as the other one. And so we'll look at those two possibilities. So if the outside alkene here picks up a proton, it would be added there. This would become a carbocation. And then the resonance would stabilize that carbocation. Oops. Put hydrogen there. And spread it out between a secondary and primary. So that's not great. Let's look at the other option. If this proton, this alkene picks up a proton, the proton would add here to the outside, allowing the carbocation to form here. So it can be stabilized through resonance. It's also in a tertiary position. The resonance stabilization Oops, didn't do that very good. Try that again. The resonance stabilization would move the carbocation here, and the double bond would shift over here. So it'll be on a secondary. So spreading out the positive charge over a secondary and a primary, not as stable as spreading it out over a secondary and a tertiary. So this is not the correct pathway. And then once the Br minus forms, after the proton is picked up by the pi system, if it comes into this tertiary carbon during the transition state, that'll be well stabilized. If it comes into the secondary carbon during the transition state, it won't be as effective as stabilizing the partial positive that stays on that carbon. So since we're at a low temperature, we want to focus on the pathway that would stabilize the positive charge during the transition state, and that's the one where the bromine attacks the more stabilized positive through hyperconjugation and induction. So that would lead to the major product. And that is a chiral center, so in half the molecules, so you could draw a solid wedge or dash wedge and then say plus an enantiomer, or you could use the zigzag to indicate that the bromine and the methyl are positioned in both potential spatial arrangements. If you're at 40 degrees, this molecule would react back. And once in a while the bromine would come in here. And since that would produce an alkene that's more substituted with carbon groups, that would be the major product. So the temperature makes a big difference there. And you want to think about what the temperature means for the reaction pathway and for which product might be formed as the major product. I'm going to skip this section. I'm pretty sure you're not going to be asked about any of this 1,4 addition in a polymerization reaction. So then the last thing we're going to discuss today is an introduction to the pericyclic reactions. We're going to talk a lot more about this on Wednesday. There are 3 types of pericyclic reactions we're going to discuss. What's interesting about them is they do not form any charges, and they also do not form any free radicals. So they're different from all the other reactions we've seen. And so there are some common themes here, and you'll see them as we go through. So the first one is called a cycloaddition. It's an addition reaction because you're adding across pi bonds. Right, we're adding across this pi system, and this pi system we're adding across there and making a couple new sigma bonds. Right, so if we were to number these, carbon 5 bonds to carbon 1 and carbon 6 bonds to carbon 4. We're making 2 new sigma bonds by adding across these pi bonds in a 1,4 addition across the alkene, the diene. So it's an addition, and it's a cycloaddition because we're creating a cyclic or a cyclohexene ring, right? So we're forming a ring by combining these 2 structures together. And what you'll notice with the mechanism here is that it happens in one step. It's concerted, meaning it's all occurring at once. Each of these pi bonds shifts around in a circle. And you could draw the circle in the other direction. So there's no necessarily directionality to that circle. This pi bond doesn't have to come down here and form this sigma bond. It could come up here and form this sigma bond. So this, one thing students do sometimes with these is forget to notice the hydrogens, right? I can't push this pi bond out here to form a sigma bond and then not do anything with this at the same time. Right? This carbon here already has 1, 2, 3, 4 bonds. So if I'm going to bring these pi electrons up to form a new sigma bond, a 5th bond to it, It can't be the only thing that occurs. It can't make a 5-bonded carbon. Right? So that's why it has to occur in a circle. As soon as one pair moves out to form a sigma bond, it would make something really unstable unless another pair moved away. And by going around a circle, it kind of completes itself. So when these electrons come up here and form the sigma bond, these could come over here and form a pi bond. And then these could come down here and form a sigma bond. And since this bond's moving away, this carbon needs more electrons. It's going to get them from down here. So every carbon that has electrons moving away from it has other electrons moving toward it. So it never forms a charge or an incomplete noble gas configuration except during the very instant of collision, during the transition state. So that's a cycloaddition. The other two are called electrocyclic reactions and sigmatropic rearrangements. So what do we see here? These are also both pericyclic reactions, which means they are also one step, and they also involve the electrons moving around in a circle, and they also you could also show the electrons moving in the opposite direction. So here the electrons are kind of shown moving clockwise. They could have also moved counterclockwise. In the electrocyclic reaction, two of these pi bonds just move one spot over and become a different pi bond. This one here ends up right here. But one of them goes from being a pi bond to a sigma. So we're seeing a pattern here. With the cycloaddition, two of these pi bonds moved out to become sigma bonds. We started with 3 pi bonds, we only ended up with 1 because 2 of them became sigma bonds. So that's the cycloaddition. In the electrocyclic reaction, we have 1 pi bond become a sigma, the other 2 pi bonds remain pi bonds. And in the sigmatropic rearrangement, again, they could go around the circle in the other direction. What we see here is one of the pi bonds shifts over to become a sigma bond. Meanwhile, a different sigma bond shifts over to become a pi bond. So here there's no net change in the number of pi or sigma bonds. And that's really the difference between addition and rearrangement, right? In an addition reaction, something is added across a pi bond, and so the pi bond forms new sigma bonds. In a rearrangement, there's no change in the overall number of pi and sigma bonds typically. So the 4 features, we talked about most of these already. For all 3 of these reactions, cycloaddition, electrocyclic, sigmatropic, they're all called pericyclic reactions because they all have a mechanism that occurs in one step, no intermediates. There's one single transition state where all the electrons are breaking and forming bonds all at the same time. There's a ring of electrons moving, so the mechanism involves the electrons moving around in a ring, in a circle. The transition state is cyclic. Right, so let's look at the transition state. We didn't do that part. So let's look at this transition state for this one. How would we draw the transition state? Well, the transition state shows any bonds breaking or forming with a dotted line. So here's the mechanism. The transition state, this pi bond's breaking, so it would be represented with the dotted line. It's moving over here forming a sigma bond, so the sigma bond will be represented with the dotted line. This pi bond's breaking, so it's represented with the dotted line. It's moving out here to form a new sigma bond. That would be a dotted line. This sigma bond isn't breaking. This sigma bond isn't breaking. The pi bond here is breaking though, so there should be a dotted line there. And it's moving here to form a pi bond, so there should be a dotted line there. So in each one of these types of reactions, there's a cyclic transition state, and there's something a little bit extra stable about that. I don't have a good explanation for it, what makes that stable. But the cyclic transition state is relatively stable transition state. It's not easy to move around 3 pairs of electrons at once, but moving them in a circle does somehow make that easier and make it a little bit more stable. And so we'd see the same thing here in this as well. So the transition state, if I ask you to draw these transition states, each one is going to involve bonds breaking and forming all the way around a ring. It doesn't have to be a 6-membered ring, but there's some kind of ring where the bonds breaking and forming go all the way around. There won't be any gaps there in the dotted lines for the transition states. And lastly, because there are no charges existing, even during the transition state, the polarity of the solvent is irrelevant, right? Normally, if you have to do some reaction, like maybe break a carbon-bromine bond, as that occurs, during the moment that the bond is breaking, it starts to form charges. So we needed, in last semester, we talked about all our reactions. We needed a polar protic solvent or a polar aprotic solvent. We need a polar solvent either way because we needed the solvent to form solvent molecules, to form some attractions here during the transition state. But since these transition states don't form charges, you don't need a polar solvent to form attractions and stabilize the transition state and increase how often the reaction can occur. And so that means we don't have to worry quite so much about our solvent choice. From a practical perspective, maybe we don't need any solvent. Or maybe if our molecules are low polarity molecules, we don't have to worry about trying to get them to dissolve in a polar solvent. So that allows for more flexibility from a synthetic perspective. And so this pretty much just summarizes what we just said in terms of the differences between these 3 types of pericyclic reactions and the numbers of pi bonds that get converted into sigma bonds. That's the main thing you're going to look for. If I ask you to differentiate between a cycloaddition and electrocyclic reaction or a sigmatropic rearrangement, the difference is going to be in the number of pi bonds that break and the number of sigma bonds that they get replaced with. All right, so that gets us into a good chunk of chapter 17. And there's a decent amount for you to practice there. As always, check your work with the solutions guide. If you're not getting things correct or it doesn't make sense to you, please let me know so that we can discuss in more detail. This material is going to be, you're going to be tested on it, not this week, obviously, but next week. So, we want to keep up with the pace of the course as much as possible. On Wednesday, we're going to focus on some specific examples of some of these pericyclic reactions. We're going to look at cycloaddition. We're going to look at some electrocyclic reactions. And then the following week, we'll get into some sigmatropic and some reactions beyond that. So on Wednesday specifically, we're only going to cover a couple sections. The electrocyclic these electrocyclic reactions are especially challenging for students. So, to give yourself the best shot at getting a grasp on those when we cover them, you want to be as prepared for those as you can be. Any questions about anything? If you have questions, feel free to unmute yourself or type something in anytime.